In the last lecture, we discussed Coulomb's law. We stated it for a single charge particle, and we said that if you have a particle located at a point, and let us say that it carries a charge q, and if I look at any point P at a certain distance t from the charge, so let me say that this charge is located at the origin of the coordinate system, so therefore it is at the origin, and this P has coordinates x, y, z, then the electric field at the point B by this charge q is simply given by E is equal to q by r squared r hat, where r hat is the unit vector in the direction of the point P. What we then did was to generalize the result to a system of charged particles by stating the principle of superposition. So what is it that we did? We said that if I have a system of charged particles, let us say q1, q2, etc., qn, and they are located at the points r1, r2, etc., up to rn. All these are vectors, and we are interested in the field at a given point r. If I am interested in the field at a given point r, this would be simply given by the summation of the fields produced by each of these individual charges. So I will write that this is equal to Ei of r. This is the statement of the principle of superposition. The field produced by the individual charges add up to find the total field produced by the collection of the charges q1, q2 to qn. And what is Ei given by? Ei is simply given by qi divided by mod r minus ri whole cubed multiplied by r minus ri. This is indeed the statement of the Coulomb law together with the superposition principle. Now, we already know from a detailed discussion in the earlier lectures that all charge is quantized. It always comes in discrete units, integral multiples of either the electron charge or the proton charge, and therefore Coulomb law together with the principle of superposition essentially completes the subject matter of electrostatics. Because you give me any charge distribution, all that I need to know is to find out the locations of the individual charges. q1 is located at r1, q2 is located at r2, so on and so forth, qn is located at rn. Find the field produced at any point from each of them. They are simply given by the usual inverse square law, add them up, and then you find the total charge. But we know this is not the end of the electrostatics. As I said in the last lecture, it is in fact the beginning of the subject matter of electrostatics, because we have continuous charge distributions. Not only do we have continuous charge distributions, materials built out of these continuous charge distributions behave very different from each other. You have conductors where the charges are free to move. You have insulators where the charges are not entirely free to move, but they can only adjust their positions against an external field. So in order to discuss this very rich physics, this very rich world of electrostatics, you have conductors, you have dielectrics, you have liquid crystals, you have ferroelectrics, so on and so forth. We need to go beyond these basic principles and develop special techniques. In order to develop these special techniques, what I did last time was to consider a toy example of a certain charge which was distributed over a certain line. So let me very briefly recapitulate that and see what is it that we have to do now. So let us take a line which is, let us say, along the x-axis, and then what I did was to take a charge q and I distributed it uniformly at discrete points. So what do? First of all, I mark the center of the line. I put a certain charge. So let me call it as q by n. Then I choose so many equidistant points here, so many equidistant points to the left of it. The total length is simply given by L. What I do is to distribute q by n on each of these points. So if there are n equidistant points, n is taken to be odd for the sake of convenience for purposes of illustration here. If there are n equidistant points, I put q by n charge on each of them so that the total charge adds to q. That is what we did. So when we are looking at n equidistant points, obviously I have the distance scale which is d, which is simply given by L over n minus 1. I am not going to write that. And then I asked what is the field produced by this line charge distribution. which is not continuous but which is discrete along a line which is perpendicular to this midpoint of the line charge. So, if this is the x-axis, let me call it as the z-axis. I take any point P which is having a coordinate z, x is equal to 0, y equal to 0, because I will put the origin at the midpoint of this line and I ask what is the field produced at this point. Now, thanks to the principle of superposition, and of course you people have worked out many such examples in your class 12, it is not at all difficult to write down the field at this particular point P. All of you know that the direction of the field is simply along the z direction. What do I mean by that? By that I mean the x component and the y component of the field identically vanish, only the z component survives. What is the expression for the field? If you people remember, this is what I wrote. E is along the z direction. Okay, this is simply given by q by n, and what I did was to pick out the first point. So, that is simply given by 1 over z squared. This is the field produced by the charge located at this particular point. Then I was interested in the fields produced by the charges which are to the right and to the left of the origin, which I wrote as summation k equal to 1 up to some m, which is simply given by n minus 1 by 2. Then I had q by n, of course, comes here because each of them carries a charge q. I have my z here divided by z squared plus k L by n whole squared to the power of q, 3 by 2. And the electric field is along the z direction, and this is the expression that I am going to get. So, you can easily see this. So, once we have done this, we have a complete expression, but that is not my purpose. My purpose was actually to explore the behavior of this field in the limiting case in various cases. For example, when z is far away from the line charge distribution and z is very close to the line charge distribution. If you people remember again, I discussed the first two cases with some generality. What is it that I did? I looked at the case when z is very large. I looked at the case when z is very small. I should quantify the statement z is very large, z is very small. The way we do that is not tough at all. What we say is that if z is much greater than the length of the line charge distribution, we say z is large. On the other hand, if z is much less than the interspacing, the spacing between the two consecutive charges here, then we say z is small. The distance of your reference point is smaller than the intercharge separation. These are the two extreme limits that I discussed. I am not going to work out those steps again, but you people can easily see that in both the limiting cases, we are going to get the Coulomb law. So, let me write that down because it is important for us. So, I say if z is very much greater than L, that is what I am interested in. If z is very much greater than L, then I am not able to resolve the size of the system. I wouldn't know that actually the charge is distributed over a line of length L. I would imagine that all of it is probably concentrated at the center. Therefore, the leading order contribution for the field will be simply given by q by z squared k. It is as if all the charge is concentrated at the origin. Of course, what you can now do is to imagine that I am going to resolve the distance or resolve the size of the system. Then I will get higher order corrections which will go like 1 over z cubed, 1 over z squared, z to the power of 4, etc., etc. We are not interested in that. We are interested only in the leading order, and this is the electric field that I am going to get. Now, on the other hand, if you go to the other limit, z is much less than d. Okay, if z is much less than d, of course, it is even lesser than L because I have put a large number of divisions on this line of length L. If I look at this, again I get the Coulomb law because what my test charge is essentially the field due to only one particular charge. So, that is again given by q by n z squared k hat. So, in one case, you see the field produced by all the charges distributed over the n points, which is the reason why I get the total charge q in this particular example, whereas here I see the field produced by only one test charge q by n, whatever is closest on the z axis, and all the others will give a perturbation. If I remember right, I even wrote down the correction terms which go like proportional to z, etc., etc. I am not going to do it now. Now, we ask a far more interesting question. what happens in the intermediate case. So the intermediate case corresponds to D less than or equal to Z less than or equal to L. Before I proceed to discuss this example, let us pause for a minute to examine what this situation means. So I am sitting at such a distance. So let me write down the figure again. I am not going to write all the points. Let us say I am going to write a few points here. So this is the intercharge separation D, and I have put my Z here. So I put my Z somewhere here, and I am saying Z is much greater than D. What is the meaning of the statement that Z is much greater than D? By that I mean that I am sitting at such a distance that to the lowest order I can ignore the separation between the two charges. So in this situation, one says that it is not going to be a great error on our part if we assume the charge is going to be continuously distributed. I am not going to resolve in the 0th order the separation between the two charges. So in other words, I am going to say that D by Z is very close to 0. That is the statement that we are making, because Z is much greater than D. On the other hand, I also have the scale Z is much less than L. So if Z is much less than L, it is as if you will never see the end points of the line charge. So the end points are sitting somewhere here. So Z by L is a very small quantity, or equivalently L by Z is much greater than 1. So in the 0th order, I can ignore the finiteness of the line charge distribution. That is, in the 0th order, the line charge can be taken to be of infinite length. Is that part okay? I am not saying that the line charge is of an infinite length, but for all practical purposes, it is of a very large length which can be approximated to infinity. And if I am going to work out higher order corrections, they will be obviously of the order 1 over L, which we will not bother about at this particular point. So we are interested in finding the electric field produced by this kind of a line charge at a location Z, which is larger than the intercharge separation, but which is smaller than the line charge separation. So what are we going to do with it? Well, what we do is to go back to the previous expression. I wrote the summation over the contribution coming from each of these charges, sum them up, but that is not what we need to do. We want to motivate how we are going to get into the notion of a continuous charge density, and so in order to do that, what I shall do is to show you the graphical representation as to how the field varies in this particular regime, and that is really instructive. So since I am going to show a few pictures for you, graphs for you, I might as well start with the simplest of the situation, and let us look at the first graph here. Now I have to explain a few notations here. If you look at the x-axis, the variation is from 0.5 to 5, which is the distance Z. So this is actually the distance Z. That is what we have here. Now I am drawing the field along the y-axis. I am interested in the E. However, what I have done is to choose a line of roughly 1000. L is of the order of 1000, and therefore when my Z is varying from 0.5 to 5, you can easily see that I am sitting very close to the line charge distribution. Now the next question that we have to ask is, what are the charges that we have played on this line of length L? What I have done is to put only 3 charges, one at the center and the other at the two ends, and I am sitting very close to the line charge. So what do I mean by that? So there is one center here, there are 2 endpoints here, and I am sitting somewhere very close. So obviously what I expect is that this figure should conform to the limit that Z is much less than D, because D is actually of the order of the length of the line charge itself. It is simply given by D by 2, L by 2, I am sorry. Now let us look at this figure. There are 2 curves actually which have been superposed on each other, because you can see some slight variation in the color between green and the red. Actually, one of them corresponds to the exact value of the field, that is the red one. You see a few red points here, whereas the other corresponds to a curve fitting. And if you look at the curve fitting, you will be able to see that it goes like 1.001 x to the power of 1.99999, which is an excellent approximation to 2. Therefore, we can simply say that E is indeed going like 1 over Z square. That is what we are seeing. So this simply verifies whatever we had actually analytically worked out, that namely if your test charge or if your point is very close to the system, okay, then all that you will see is the field produced by one individual charge. Now let us proceed a little bit further. Let us again keep only 3 charges and let us ask what happens if I go a little bit farther. So that is something interesting, and this is what we are going to get. Now what I have done is, again I am keeping the same number of charges, but you can see my Z is varying from 5 to 50. So earlier Z was varying from 0.5 to 5. Now I have 5 less than Z less than 50, which is still very small compared to the length, something of the order of 1000, but still a careful curve fitting shows you that there are slight deviations. In the first case, we had got n is equal to 2. Therefore, if I wrote E is of the order of 1 over Z to the power of n, in the previous case, we got n is equal to 2. Here, we are getting n equal to 2.00679, which is a slight deviation from the value n is equal to 2. So, although the distance is small, it is not as small as the earlier case, and therefore, the deviation from the 1 over Z squared behavior is already something that you can see. Now, the next thing to do is to, of course, to the next figure. Here, what has happened is that I have gone to a scale which is comparable to the length. It is still not large comparable to the length, because please remember L is of the order 1000. That is what I have, and here my Z is all going all the way up to 500. If you look at the final value, now you see that there is a major deviation. How does the exponent behave? Again, if I write E is going like 1 over Z to the power of n is of the order 1.3, which is quite far away from 2. The interesting thing is that nowhere do you find a behavior something like 1 over Z unless I considered a very, very narrow regime, which I am not doing. Therefore, in order to complete the tail for this particular example, let me go to the next case where I make Z even larger and ask how the field behaves. This is the last of the thing. Here I am now going to a length which is only between 500 and 550. It is still not very large compared to the size of the system. It is only comparable to the size of the system, but already E, if I write again, goes like 1 over Z to the power of n is of the order 1.93. So in other words, if I had continued this experiment, continued this computation, and gone to L values between, let us say, 1000 and 2000, or 10,000 and 15,000, let us say, which are really large compared to the size of the system itself, then we could have said that n would have approached the value 2. So what is the statement that we are making? For this simple example, what we find is that n extrapolates between 2 and 2. So n initial was equal to 2 when Z was very, very small. N final is also equal to 2 when Z is very, very small, and depending on the number of charges that you put, there will be a small window in which actually n will pass through 1. That is, the field behaves like 1 over Z. Now, it is deliberately that I did not show the regime where field behaves like 1 over Z here, because I have put only 3 charges. Therefore, it is a very, very narrow window in Z. Is that okay? Between Z1 and Z2, which is a very small number, which is very difficult to show. And therefore, what I will do is that in order to illustrate that, I will go to the next figure. In this next figure, what I have done is to put 10 charges. When you put 10 charges, I am not interested in the extreme cases when Z is very, very small or when Z is very, very large. I am interested in the intermediate case where Z goes from 0 to 50. As you people can easily see, now what is happening? I am going to concentrate entirely on the value of the exponent, and as you people can read, you see n is of the order 1.112, which is precariously close to n equal to 1. It is not quite 1, there is something like a 10% error, 10% deviation, but still the minute I put 10 charges, it became n equal to 1.1.2, whereas when I had put only n equal to 3 charges, that gave me some exponent something like 1.4. That is something that you have to remember. By the way, when I say 10, actually I have put 20 charges, 21 charges to be precise. When I say n equal to 1, I have put 3 charges. Now obviously a nice question to ask is, what would happen if I could refine my calculation even further? Now what I shall do is to divide the line into 1000 equal intervals. So you have a length of the line of length L. I shall put 2001 charges. Is that okay? I will divide it into 1000 divisions to the left, 1000 divisions to the right. Therefore, the distance between them is of the order 1. If I did that, again, if I look at the regime between 5 and 50, now this is a very beautiful regime because D is of the order 1, L is of the order 1000. And what is my Z varying from? My Z is varying from 5 to 50, and it eminently satisfies the condition that D is much less than Z less than L. And lo and behold, what is it that you find for the exponent? Again, if I parameterize, E goes like 1 over Z to the power of N turns out to be 1.02709. Please remember that when you are staring at this curve, there are actually two curves. One of them is red, another is green. The red curve is the exact number obtained by summing over all the charges. This has been done numerically. The green curve is a curve fitting and it is giving a number 1.02709. Whenever I fit a curve, whenever I make a statement that n is equal to 1.02709, it cannot be an approximate, it cannot be an exact number. So I have to place the error on it. The error on it, in fact, is remarkably, the error bar is remarkably stringent. What we are saying is that this is equal to 1.02709 plus or minus 10 to the power of minus 8. So it is a very, very accurate representation, and people can easily see that if I had replaced n1000 by n2000, n equal to 10,000, that is, if I had put 21,000 charges of that same length, then what would have happened? D would have been of the order of 0.5 and n would have been even closer to 1. So what is the theme of my discussion? The theme of my discussion is that irrespective of how many charges you have and what the division is, that in the asymptotic limit, when the z is very, very small, when the z is very, very large, you have n equal to 2. But between n equal to 2 and n equal to 2, the exponent actually decreases. So let me illustrate that schematically. Let me draw a curve, or for that matter a series of curves which illustrate my point. So what I shall do is to consider the z here, and then I have the exponent n. N is a continuous function. Okay? Now, suppose there were only 3 charges which were distributed over the line n. Then I know that when z is very, very small, then n is very close to 2. So this corresponds to n equal to 2. When z is very, very large, let us say, so this is the n equal to 2 line. So this is going to be like this. What was the first example? We put only 3 charges on that line. So of course, when we were very close, n was very close to 2. When we were far away, n was very close to 2. Please mind, I am not plotting the field as a function of distance. I am plotting the local behavior of the field. So I am going to write E of z goes like 1 over z to the power of n, and n itself is going to change from point to point. How far you are going away, how far you are. Therefore, this object itself is a function of z. That is what we are going to show. So if n were equal to 2, or n equal to, if I had only 3 charges on this one, which I will illustrate by putting a capital N. So suppose n equal to 3. That is, I have put 3 charges on the line L, then your curve would have gone something like this. It will be remaining very close to the value of n equal to 2. It will dip a little bit and again reaches asymptotic value. But on the other hand, when I looked at a case like n equal to 1000, what is it that happened? The value starts with n equal to 2, comes down, stays in some region for a long time, and then it goes up. So let us make it this way. And now, if you look at this region where the behavior is roughly constant, this would correspond to n is equal to 1. That is the statement that we are making. This in fact is asymptotic because as n goes to infinity, there will be a certain region. Okay? In our case, it corresponded to the distance from 0 equal to z equal to 0 to z equal to 5 to z equal to 50. There, my n behaved like 1. That means my electric field is actually behaving like 1 over z. This is the point that I wanted to simply make. Now, all of you are already familiar in finding out the electric field given a certain charge distribution. All of you know how to find out the field produced by an infinite line charge distribution, infinite surface charge distribution, a spherical charge distribution, so on and so forth, by using Gauss's law or by even by direct integration. And all that I am doing is to sort of rederive, although approximately, although numerically for you, using these techniques. Okay? And why is it that I am doing? And that is something that needs an explanation. Okay. Now, I made a statement that when n becomes very, very large, for example, n equal to 1000, the spacing between the charges is very, very small, because the spacing is of the order d equal to L by n. So, as n becomes very, very large, space becomes very smaller. And now, if z is much, much greater than d, of course, I want z to be much, much less than L, let us remember that, then I made a statement that I am not going to resolve this operation. If I am not going to resolve this operation, however, if I know that it is distributed over a certain length L, that means I am indeed approximating a discrete charge distribution by a continuous charge distribution. So, what are we saying? In this regime, when z is much, much greater than d and z is much, much less than L, okay, if d is very small compared to L, that is, if this capital N is very, very large, then I can replace discrete charge density by a continuous charge density. Therefore, I automatically get a line charge density lambda z, which is equal to lambda naught, which is nothing but q divided by the length of the system. Okay. Now, the rest is all a matter of very simple integration for you people to perform. You are given a uniform line charge density. Since z is very small compared to the total length, you can take the total length to be infinite. Therefore, you integrate it from minus infinity to plus infinity. So, at any given distance, the field obviously behaves like 1 over z, and that is indeed the result that we have derived. Why is it that I spent so much time? The reason is that we should be able to make sense physically out of apparently two contradictory statements or principles. We stated that all charges come in integral multiples of the electron charge. Therefore, charges can only be discrete. But on the other hand, in everyday examples, whether it is dielectrics, conductors, method of images, whatever it might be, we always deal with continuous charge distribution. So, to make sense out of the statement that there is a continuous charge distribution, although the underlying charges are discrete, we have to understand exactly what kind of an averaging that we are doing. In order to motivate for you the idea of an averaging over the length scales, the idea of the fuzzy nature, how the discreteness going to the continuous nature, I gave this particular example. Now, let me make these concepts more precise. What shall we do that? Now, again, let me draw this line for you, and I have the line perpendicular to that. I have various charges sitting here, and I sit at a distance z, which obviously satisfies my condition. So, this separation is d, the total length is L, so I have d much less than z, much less than L. When I say that my z is so large that I cannot resolve the distance between them, and therefore it appears as if it is a continuous distribution, by that I mean something more. What is that? Suppose I calculated the field at this point z and I move a distance z plus epsilon. This is exaggerated. If this epsilon is of the order d, that is, I have the electric field at a point z, I have the electric field at a point z plus epsilon. Epsilon can be positive or negative, and epsilon is, if it is of the order d, I should not find any appreciable difference in the value of the field. What do I mean by the appreciable difference? By that I mean, if I have a measuring apparatus, okay, some test charge that will actually sense the value of the electric field at that particular point, it should not have a resolution that actually distinguishes the value of the field at z and z plus epsilon. That is what we say. That means that my test charge does not have the sensitivity of saying that this charge is located here, this charge is located here. It sees only some kind of a uniform charge distribution in between these 2 points. Or if you want to imagine, you can even think that your test charge itself has a certain size. After all, test charges are not point particles. They are also macroscopic objects in everyday experiment. So, if the size of the test charge itself is comparable, Okay, so I am going to put a test charge here. Let us say this is my test charge. If that itself is comparable to D, then what you are going to measure is only the mean field over the distance of the order D, and then average over that. That is completely consistent with the fact that I am replacing a discrete charge density by a continuous charge density. I will get consistent results. Okay. Otherwise, of course, strictly speaking, mathematically speaking, speaking hypothetically, if you give me a test charge and an electrometer, let us say, of infinite accuracy, then I would have been able to see the what? The discrete nature. But when we are speaking of continuous charge distributions, this is what we have in mind. What we have is that the distances are sort of intermediate between the size of the system and the separation, and my averaging procedure ensures that I do not have that kind of an accuracy. Even if I had that kind of an accuracy, it is not of much use to me. This is not unfamiliar to you people, because we know that deep down all atoms and molecules are discrete, yet when we speak of the sliding of a box or some other thing over an inclined plane, like in your mechanics example, you treat as if the coordinate is a continuous coordinate. Okay? So that is the kind of situation that we are dealing with. So what I will now do is to formalize this statement so that we all understand what we mean by a continuous charge distribution. What is it that we have to do? The first step is to get into the notion of a continuous charge distribution from the discrete charge. So how shall I do that? The way to do is to consider a point z, or x for that matter, because I am looking at the x-axis, and I replace the value of the charge at the point x by an average over the neighborhood of these points. Let me write down the expression for you, and then I will explain that. So I will write it, this is nothing but 1 over a, that is what I have here. So I will write x minus a by 2 into x plus a by 2 qi. So what do I mean by that? All that I mean is the following. So I have my charges sitting here. What do? I take this point x. I know that there is a charge sitting there. If I move slightly away, there is no charge sitting because the charges are discrete. However, I will choose a suitable interval a. How you are going to choose your suitable interval a depends on the least count of your measuring apparatus, depends on the desired degree of accuracy of your measurement of the field and the charge density. It is dictated by how macroscopic or how microscopic your calculation is. So whatsoever it may be, let us say that this interval is of the order a, is of the magnitude a. What I do is to sum over all the charges in this interval a. In our case, there were equal number of charges. It may not be equal number of charges. In that case, we get what? Non-uniform charge density. So sum them all over, divided by the length, that will give you the average density at this point x. Now if I am interested in the value of x at some other point, let us say here, then I will construct an interval around this point. If I am interested in the value of x here, I will construct an interval here, all of length a. I perform the averages and then replace them by appropriate continuous charge densities. Therefore, in order to emphasize that, I can even put a bar. How do I generalize it to surface charge distributions and space charge distributions? Not difficult at all. What we shall do is to say that rho at any given point r, that is what I have here. What shall I do? I will take a certain volume and sum over all charges in a given volume. Okay? All charges in a given volume that surrounds r. So imagine that r is sitting at the center of U cube of length a. Then you sum over all the charges which are sitting inside the cube divided by this particular volume. Then you are going to get the surface, the space charge density, and in a similar manner you can go on to do it for current densities later, or for that matter surface charge densities. So we know how to go precisely from a discrete distribution to a continuous distribution. By the same way, you people should remember that electric fields can also be defined. So if I were to calculate the mean value of the electric field in my particular example, what would that be? This of course is a one-dimensional case. I will write 1 over a. It need not be the same a as this, but it is convenient to choose that. That will be z minus a by 2, z plus a by 2 e of z bar dz bar. So what am I doing? I calculate the electric field at every point in the interval z equal to from z minus a by 2 to z plus a by 2. I sum over them and divide it by the total length. I get the mean field. So when I say that I am approximating the discrete distribution by a continuous distribution, I should imagine that the electric fields measured are also written in this particular manner. Once this particular concept sinks in, the rest of it is quite straightforward and easy. This might appear to be pedantic at this particular point, but if this particular concept did not sink in, then we will end up with a variety of so-called apparent paradoxes, contradictory statements, where we do not understand the physics completely. So that is the reason why I have spent some time. Now what I shall do is to go on to employ the concept of a continuous charge distribution to write down Coulomb's law in its differential form, the so-called Gauss's law, which is very, very important and very, very useful. Once we understand the meaning of continuous charge density, it is not at all difficult to write down the electric field produced by a continuous charge distribution. What shall we do? Let me take a region R. This is a region R, and in this are charge distributions. They need not be uniform here, but it is a finite charge distribution. That is something that I am emphasizing at this particular point. So what is it that I have here? I have rho given as a function of R prime, where R belongs to the region R. Let us remember that. Now I am interested in R. So what is the desired thing to be evaluated? I want to calculate E of R. In writing E of R, we are not going to place any restriction on the value of R. It can take all possible values, just as in the case of point particle also, it was able to take all particular values. However, when we worked out the field produced due to a point particle, what is it that happened? What happened was that we were not allowed to sit on the point charge, because at that particular point the field blew up. So we were always to stay carefully away from the location of the charge itself. You can go arbitrarily close to the point charge and the field would diverge as 1 over r squared. But here you are allowed to enter the charge distribution. In other words, there is no restriction on the values of this r. Let us remember that. And yet we are not going to get fields that are going to blow up because of our peculiar averaging procedure, which is the right thing to do. So what is this electric field given by? The electric field is simply given by a superposition principle. All of you know how to write that. So that is nothing but rho of r prime d cubed r prime divided by mod r minus r prime square cubed, let me write that, and r minus r prime. This is nothing but a continuous version of your discrete statement of the Coulomb law. Rho of r prime d cubed r prime is the infinitesimal charge sitting in the volume surrounding the point r prime. So that infinitesimal charge is producing this particular field. That is all the statement is, and we are going to integrate over all r prime, obviously in the region R. This is the electric field. Now given this electric field, obviously the great advantage is that I do not have to perform a tedious summation. A whole world of analytic techniques will open for us, because we can use symmetries, we can perform integrations, we can study various limiting cases, we can study macroscopic electrostatic phenomena, which we are really interested in, and in that sense it is a major boost for us in our study of electrostatic phenomena. But now, right now my purpose is actually to use this electric field produced by a continuous charge distribution to rewrite Coulomb law in a slightly different form, the so-called Gauss's law. That is something which is very, very important for us. In fact, this is a prototype for many, many other theories. This is something which was written even for the gravitational field by none other than Laplace. And now what we shall do is to see how to rewrite Coulomb law, which is 1 over r squared, into a differential form for the electric field, and we shall do that step by step. Let me consider a charge distribution in a region R. So there is a certain charge distribution rho of r in a region R. Now I am interested in the divergence of the electric field produced by this charge distribution. So what are the steps that I am going to do? I have my electric field which is given as a function of r everywhere. So let me make it r prime here. Then what I will do is to look at divergence E at every point r. We have not yet done that even for a point charge, although I have hinted at what its form would be in one of my earlier lectures on the divergence theorem, Gauss divergence theorem. We will revisit that now in a minute. Then we shall ask, what about the flux that goes out of any given volume? In order to simplify matters, I shall consider various special cases before stating the general result. So if this is my region R, let me consider another region R prime. So this is another region R prime. This region R prime is disjoint with R. Okay? What do I mean by that? There is no overlap between the regions R and the R prime, which is the reason why they are separate. Therefore, if I were to take my electrometer and move in this region R prime, I am not going to find any charge. Therefore, this region has no charge. No charge does not mean no field, because we know that even a point particle situated in this region would actually produce an electric field everywhere. Therefore, there is going to be a non-vanishing electric field in this particular region, and we are obviously interested in what the electric field is and what the divergence of the electric field is. So, please remember this geometry well before I proceed to write down the next step. What would be the value of the electric field? My electric field at any given point R in the region R prime, so let me emphasize that here, is simply given by rho of R prime d cubed R prime divided by mod R minus R prime cubed into R minus R prime. You people are quite familiar with this result. Of course, R prime belongs to region R. That is something that we have to remember. Okay. In general, since you have not given me the charge distribution, I do not know how to calculate the electric field. However, although I do not know what the value of the electric field is, I do know what its divergence is. That is something that we have to remember. What is the divergence of this electric field in this region? Divergence of R in the region R prime. That is something we should not forget. Remember, the continuous charge density is nothing but an approximation to what? A large number of discrete charge densities, discrete charge distribution. Each charge is going to produce an electric field which goes like 1 over R squared. That is what this relation is telling me. Therefore, by principle of superposition, if I know the field produced by different point charges in the region R, find out the divergence coming from them, add them up, I will get the total divergence. Therefore, if I could write it sort of symbolically, this is nothing but summation divergence EI of R, where I is the what? The contribution coming from the ith charge. Of course, if you want to write it in terms of what? In terms of the continuous charge density, you will replace it by an integral. Let me not do that. What matters is the concept. And how does this EI of R go like? EI of R goes simply like 1 over mod Ri minus R whole squared. And then of course, I have the unit vector R minus Ri. So, I have the unit vector corresponding to this. It is a very simple exercise for you people to find out the divergence of this function EI. So, I will leave it as an exercise for you people to work it out. You can check that divergence EI is identically equal to 0. Please remember, this R is located away from the point where the charge is located. What am I saying? These Ri's belong to the region R. The points R belong to the region R prime. R prime is disjoint from R. In other words, I am not evaluating the divergence wherever the charge is located. Therefore, a simple evaluation of this divergence EI, all that you need to do is to substitute for the divergence in the spherical polar coordinate system. If you did that, this would be identically equal to 0. Therefore, by principle of superposition, I conclude that divergence of E at any given point R through the whole charge distribution is also 0. This was coming from an infinitesimal charge element. This is coming from the total charge element because, so let me write it explicitly, because R and R prime are disjoint. So, although we do not know the detailed form of the electric field, it can be as complicated as it can be. It might be impossible to evaluate it analytically. You might have to evaluate it only numerically. Never mind about that. I know for sure that divergence is equal to 0 in the region outside. So, to summarize, I had my charge distribution in this region R. I am going to look at the electric field in this region R prime. So, this is where rho is, this is where my electric field is. I claim, irrespective of the nature of rho, how you distributed it, what you did with it, how much charge you put, I know that divergence is equal to 0 in the whole volume. Mind you, I do not have to specify what this R prime is. The only condition is that R prime should be away from R. It should not be the same as R. It can be in fact even as close to R as you want, but there should be no overlap. Once you note that divergence is equal to 0 throughout the volume, what I can do is to actually integrate this divergence over this volume. So, I will write divergence E d cubed R over this particular volume. Okay? So, that I will indicate it by the region R prime. And now, Gauss comes and tells us that this is nothing but the flux of the electric field around the surface. So, you have the region R prime which is bounded by the surface S prime. It is quite a complicated surface. Look at this. What is this? By Gauss divergence theorem, which we have actually demonstrated it for a cubical volume and a cubical surface in our earlier lecture, is simply given by the surface integral over the surface S prime, integral E dot Ts prime, but then the left hand side is equal to 0, therefore, so is the right hand side. That is what we have. This is the statement of Gauss divergence theorem. That divergence is equal to 0 is a consequence of the Coulomb law. Therefore, integral E dot ds prime over arbitrary surface equal to 0 is a consequence of Gauss divergence theorem, provided this surface S prime does not enclose any charge. This is something that I have been repeating often, so that is something that settles in you completely without any confusion. Now, once we state that E dot ds prime equal to 0, we are making an interesting statement about the flux. We are saying that, look here, this charge density is going to produce an electric field, and if I say that the field lines are entering this particular volume, okay, it need not be perpendicular, it can enter any way it wants, and some of the field lines will obviously be going out. What this statement says is that whatever flux enters this particular volume also flows out. Remember what we said about the flow. If there is no source, if there is no sink, the total flux to enclosed is 0 because it is something like an incompressible fluid. If it is incompressible, whatever gets in also gets out. That is exactly what is happening. And this statement, some kind of a conservation, whatever gets in is also going to get out. Nothing is going to get accumulated. Nothing is going to get lost, irrespective of the nature of the boundary that encloses this volume. Okay? Irrespective of the nature of the volume is the statement of this theorem. Now, of course, this is not going to be of much help to me unless I look at the overlap of this region R prime with R. If we did that, then obviously divergence E d cubed R will not be equal to 0. By the same token, integral E dot ds will not be equal to 0. If we stated that result, then we would have stated what divergence is everywhere, what integral d dot ds is everywhere, however small the volume element may be, however large the volume element may be, whatever the shape of the surface may be, and that is what leads to Gauss's law. And we shall do that now. In order to write down Gauss's law, again, it is convenient to make use of the principle of superposition. Without principle of superposition, we would be nowhere. So, let me start with a point charge. Whenever I have a point charge, it is convenient to locate it at the origin, or to put it more precisely, choose the origin of your coordinate system on the point charge itself. So, let me do that. So, I have the x and the y and the z axis. I do not have to write them down, and here I have put a charge q. Now, what I shall do is to consider a sphere of radius r which is surrounding this charge. So, this is a sphere of radius r, and I am interested in finding out the electric flux. Okay. What is the field produced by the point charge? E is simply given by q by r squared r hat, because I have located it at the origin. Now, again, let us calculate the divergence everywhere. What am I going to get? A simple calculation will show you that divergence E at any point r equal to 0 unless r is equal to r 0. At r equal to 0, your field is going to blow up like 1 over r squared. So the derivative at this particular point does not make sense at this juncture. We are going to make sense in a short while. Is that okay? We do not know how to find out the derivative because the value of the function itself is blowing up. So in order to be very careful, we say divergence r equal to 0 unless r equal to 0. However, if I were to construct a sphere of radius r as I have done now, the electric field everywhere on this sphere of radius r. So how does my electric field look like? It is going to be radial. If I take a positive charge, it is going to be radially outward. If I take a negative charge, it is going to be radially inward. This is a well-defined object. This is a finite object. Therefore, I can evaluate integral E dot ds without any problem, because I am sitting at a finite radius r where r is not equal to 0. So let us do that. So if I were to write down integral E dot ds at a radius r, okay, a sphere of radius r. So what is that? My surface element is simply given by sin squared theta d theta d phi at r squared. So I have q by r squared because I am evaluating at a fixed r. This small r will attain the capital, this one. Then I have my r squared integral d omega, which is nothing but sin theta d phi, which will turn out to be 4 pi q. That is what I am going to get. Unfortunately, I have not been very careful in writing down these expressions. Now let me fill in all the details which I had sort of omitted. This is not exactly q by r squared, but it multiplies a factor 1 over 4 pi epsilon naught. So that gets inherited here. So you get a 1 over 4 pi epsilon naught here. Now let me put a 4 pi epsilon naught here. This is nothing but q divided by epsilon naught. Okay. What are we saying? Divergence A equal to 0 at all points except the location of the charge. At the location of the charge, I do not know how to evaluate the divergence A. If I were not ambitious, if I did not wish to make sense out of Gauss divergence theorem, I would have said divergence is not defined at r equal to 0. However, I do not want to stop at that, obviously, because I want to write something called the Gauss law, right? Coulomb law in the version of Gauss's law. So what I do is instead evaluate the surface integral E dot ds, which turns out to be nothing but q by epsilon naught. The remarkable fact about this expression is that this surface integral is independent of the value of r. You can take this sphere r as large as you want, as small as you want. I can shrink the sphere to an epsilon value. Okay? The only condition is that you should be non-zero finite number, or I can bloat the sphere to a very large number. Never mind, this point charge is like a luminous source which is emitting radiation. Is that okay? Therefore, if you are interested in the total intensity, okay, like a bulb, total power emitted by that, then it is going to be independent of the surface. It is only that the angular distribution becomes smaller and smaller. Is that okay? Because as I go farther and farther, the area of the element becomes larger and larger. Okay? Apart from that, it is always given by q by epsilon naught, which is a measure of the strength of the source of the electric field. That is what we are trying to say, and that is what we find. So independent of, so please remember, independent of how small or how large the radius is, I have integral E dot s, which is equal to q by epsilon naught, which is not going to be equal to 0 provided q is not equal to 0, provided the sphere is going to enclose that. Let us just remember that. What I shall now do is to consider a slightly different situation. I shall not consider a spherical surface, but I shall consider a complicated surface. So to repeat, let me rewrite the diagram. I have a charge located at the origin, and I now consider a volume which is bounded by a complicated surface like this. Well, divergence is equal to 0 everywhere except at r equal to 0. That follows simply from the Coulomb law. But I cannot evaluate integral d dot ds, because in the original case when I wrote down a sphere, so let me write down a sphere here again. This is my sphere, okay, of radius r. This is a sphere. Let me make it explicit because it does not look like a sphere. Here my electric field was perpendicular to the surface everywhere. Therefore, I could actually evaluate the surface integral. However, for example, if you look at some particular point like this, you see, if I were to draw a line from here to here, okay, you see the field line is not normal to the surface. Therefore, integral d dot ds is something that I do not know how to evaluate. Since I have not specified the functional form of the surface, it appears that I don't know how to do the surface integral. So I have complicated my life a wee bit, only a little bit, in order to illustrate something for you. What shall we do? What we shall do is to look at again this whole region R. Okay, what is my whole region R? Whatever is enclosed by the surface S. The surface S is enclosing the region R. S is enclosing R. Now this region R shall be split into two parts. One is the interior region, which I shall call R1, which is spherical. So R1 is spherical, R2 is the intermediate region. Therefore, this region, what I have written here, this is R1, and this annulus, what you see here, annulus like thing, is R2. Okay. Now, let us look at the electric field in the region R1 and in the region R2. I know what integral E dot ds in the region R1 is. Integral D dot ds in the region R1 is nothing but q by epsilon naught. What is integral E dot ds in the region R2? Is that okay? Integral E dot ds in the region R2. Well, you might not know how to evaluate the surface integral, but so what? In all of R2, divergence is equal to 0 because the charge is not located in R2, the charge is located in R1. Therefore, since divergence is equal to 0 by Gauss divergence law, this is identically equal to 0. So we have shown that integral d dot ds is equal to q by epsilon naught if it is in the region R1, integral d dot ds over the region R2 equal to 0. And in fact, in order to make life even more clear, in order to make the concepts even clearer, I can construct a bigger region R3 which is also spherical. Okay? This is spherical again. Okay? This is R3. Over the region R3, again you will find that the surface integral is not equal to 0, but it is given by q by epsilon naught. So what can we conclude from this? Since the electric field is like an incompressible fluid, since the fluid is going like 1 over r squared, since whatever flux enters a volume, it has to leave, we can, from these three examples, an outer sphere and an inner sphere and an arbitrary surface which is enclosed in between them, we can conclude that the value of integral E dot ds should be independent of the nature of the surface. It really doesn't matter whether you take the spherical surface, it really doesn't matter whether you take a more complicated surface, it is not a property of the surface, it is simply a property of the charge that is encloses. So the first step that we have taken is to state a very beautiful result, namely integral E dot ds has a value independent of the nature of the surface. It depends only on how much charge it encloses. What I shall do in the next lecture is to use this fact to state Coulomb law in a differential form, namely divergence E equal to rho by epsilon naught, and that is what allows us to solve many problems.